In this video, we're going to explore polar coordinates and what their graphs look like. So if we think about some of the equations that we use, it's almost near impossible to write the equation in Cartesian or XY. If we introduce a new coordinate system, polar coordinates, it makes something that's almost difficult, near impossible, to describe with a Cartesian equation and make it be fairly simple. So when we're talking about a polar system, we have a pole and we have a polar axis. We also have this angle of rotation theta, and we have how far out we're going to go. We call that r. So if we were plotting the point 3, 5 pi over 3, then you would go out 3 rings and you would rotate off the polar axis 5 pi over 3. So it would look something like this. Now, if you look at a polar graph, you have all of these rings, this being my first ring, this being my second ring, and this would be my third ring. So you have these rings. Instead of being so far in the x, so far on the y, you go out so many rings and then a rotation. We now can have a negative on our r. What a negative does is do a reflection across the pole. A reflection of pi, or 180, across the pole. So if I need to go to negative 2 pi over 4, then I'm going to go over to rotate pi over 4. I'm going to go out those 2 rings. And then I'm going to reflect across the pole because of the fact this is a negative. And so here's my final point. Polar coordinates in and of themselves are not unique. I can describe this point right here as the point negative 2 and then pi over 4. I can also describe this as 2, 5 pi over 4. This point will land in the exact same place as negative 2 pi over 4. So when you're thinking about these points, these polar points, we can get there in more than one way. Any coterminal angle to this with a radius of 3 will also get me to this point. Any coterminal angle to this with a negative 2 as the radius will also get me to this point. So let's take some time to point these polar coordinates, and then let's see if we could figure out another way to get there. So 3 pi over 6. So I'm going to go out 3 rings, 1, 2, 3 rings, and then I'm going to rotate to pi over 6. So this is the point A. So I go out 1, 2, 3 rings, pi over 6. This is the point 3 pi over 6. Now I could have got there with a negative rotation, so I could have negative rotated negative 5 pi over 6. That would have got me over here, and then I could have done a negative 3. That would have done a reflection over the pole. So these are equivalent in the fact that we start and end in the same place. So how about 2, 180? So 2, negative 180. So I'd go out 2 rings. So 1, 2 rings. I would do a negative rotation, just like we expect a negative rotation of 180, or in other words, pi. So I end up right here. So 2 rings out, 1, 2, and right there. So here's where I have the 2, negative 180. I could have got there also with a 2 and 180. Could have also got there as a negative 2 and 0. So there's multiple ways of getting to the same point in polar equations. They're not unique. So then this one is what we did up here. We did negative 2 pi over 4. We know there's other ways of getting there. So I'm going to do negative 2 pi over 4. I go out 2 rings, go to pi over 4, and then I reflect across the pole. And so that's where this point lands, negative 2 pi over 4. If I were to superimpose the xy plane, the xy Cartesian system, onto this graph, then it would actually be that line worked. Good. And this line, this would be the y-axis, and this would be the z-axis. So we have a relationship between polar equations and points and rectangular equations and points. The way that we get to those rectangular equations and points, and why is that line, I want that line to go with there. So I'll just move it over here, move this line over here. Why is that line? Oh, okay, there we go. There it is. It's still kind of there and annoying, but whatever. Okay, given a point P on the plane in the Cartesian x, y, the polar coordinates are theta. These are my relationships. X is equal to r cosine theta. Now this makes sense because remember how we define the cosine of theta as being the x value over the r value. So if we just solve for x, we're going to have r, the cosine of theta, is equal to x. Similarly, if we tell you that the sine of theta is equal to the y value over r, then r, the sine theta, is equal to y. So that's where those two replacements come from. Now I also know that the equation of a circle centered at the origin is this equation. X squared plus y squared is equal to my radius squared all day long. So that's another nice replacement. If I'm trying to find an angle, I can use this ratio. Remember that the tangent of theta is the y value over the x value. So if I'm trying to convert from rectangular to polar or polar to rectangular, then I'm going to use these values. I'm going to have r is equal to the square root of x squared plus y squared. And I'm going to, by default, to use r being positive. I can have r be negative because r now does not mean necessarily a distance. It's more like rings, and we can do negatives. So, but I'm going to, by default, use r to be positive. And I'm going to use tangent of theta when I need to is y over x. And of course, x is equal to r cosine theta all day long. And y is equal to r sine theta all day long. So if I'm trying to convert these polar coordinates into rectangular, then I have to identify what I have. This is my r. This is my theta. X is equal to r sine, or cosine theta. So x must be equal to 2, the cosine of pi over 2. So x is equal to the cosine of pi over 2 is 0. So this is going to be 0. Y is equal to r sine of theta. So y is equal to 2, the sine of pi over 2. So y is equal to 2 times 1, or just 2. So this ordered pair in polar form is equivalent to the ordered pair 0, 2 in the Cartesian or xy plane. So I'm going to go ahead and stop the video, and then I'm going to give you the answers for these other ones. So I want you to go ahead and do these other ones, and then check back in. Welcome back. Hopefully what you've got for B is the ordered pair 2, 0. Now don't forget that when you do the cosine of pi, it is -1. That's why it's -1 times -2 is +2. For this one, hopefully what you all got for the answer is -3/2, square root of 3/2. And then for the last one, -1/2 and then +1/2. Don't forget that when you take the cosine of a negative angle, this is equal to the cosine of that angle. So hopefully that's what you got. Now what we're going to do is we're going to convert rectangular coordinates to each of these polar coordinates. So again, I'm going to use the fact that I have the tangent of theta, because I'm going to need my angle, is going to be my y value over my x value. In this case, I have 4/4. So in other words, I have the tangent of theta is equal to 1. This is in quadrant number 1. So the place in which tangent of theta is equal to 1 in quadrant number 1 is when theta is equal to pi over 4. Now all I have to do is find my radius, and I find my radius is r is equal to the square root of x squared plus y squared all day long. So this is going to be 16 plus 16, or in other words, it's going to be 4√2. So this point, which is 4 comma 4 in the Cartesian, is equivalent to 4 root 2 comma pi over 4. Now, I love B and D. I love me some B and D. And the reason I love B and D is because this is a quadrantal angle, and this one's a quadrantal angle. So I don't even have to go through all the shenanigans. I just have to figure out where that quadrantal angle is. So 0 comma 5 is right up here. So I am at a radius of 5, and the angle is pi over 2 because I'm straight up. So that's nice. This one is right here. It's negative 2 comma 0. So it has a radius of 2, because that's how far you're out from the origin. So 2, and it's pi. Now remember, I could have came up with a negative 2, 0. It would actually be the same thing because polar equations or polar points are not unique. Now the one that I'm going to have to do a little bit of work on is this one. So first of all, I have to remember where I am, because when I take the tangent inverse, it may give me the wrong angle referencing where I am. These are both negative. Both the x and y are negative, so I'm in quadrant 3. So I have to keep that in mind when I do the tangent inverse. So the tangent of theta is equal to my y value, which is negative 2, the square root of 3, over my x value, which is negative 2. This gives me a positive square root of 3. So I ask myself, the tangent of theta is equal to the square root of 3 in quadrant 3. What is the angle? Well, that angle happens to be 4 pi over 3. If I did not know that, I could always do the tangent inverse. If I did the tangent inverse of the square root of 3 is equal to theta, because the tangent inverse is only defined in quadrants 1 and 4 with a negative rotation, this would have gave me this as an answer, which is pi over 3. However, I would then have to change that into the correct quadrant. I'm in quadrant number 3. If I do the tangent inverse, this is not in quadrant number 3. So I would have had to use that as the reference angle to get my true answer, which is 4 pi over 3. That's in quadrant number 3. That's the actual angle of rotation that is formed by these two numbers, this ordered pair. So now that I've found my angle, all I have to do is find my radius. And again, x squared plus y squared is equal to r squared all day long. So r is equal to the square root of negative 2 squared, and then plus negative 2, the square root of 3 squared. So I'm going to have the square root of 4 plus 4 multiplied by 3. So I have a 4 plus 12. You probably already got this in your head, but I just had to write this out. Sometimes I have to do that. So my radius is 4. So my answer for C, this answer, when I get done, is going to be a radius of 4 and 4 pi over 3. And that's my final answer for C. Now we're going to take some time to convert from rectangular to polar and back again. We use, again, these three things plus this r. X is equal to r cosine, y is equal to r sine, and tangent of theta is equal to y over x, and r is equal to the square root of x squared plus y squared. Now, as I take a look at this, I need to have an r right there. I need r cosine theta. I don't have an r. So what I can do is, since this is an equation, is I can multiply both sides by r. When I multiply both sides by r, I get r squared is equal to 4r, the cosine of theta. Now, this part is x. This part is x squared plus y squared. So what I have is x squared plus y squared is equal to 4x. Now, if I wanted to, because this is an equation of a circle, I could go ahead and put it in standard form. So I'll take a moment to do that. So I have x squared minus 4x plus something, so I have to complete the square, plus y squared is equal to 0 plus that something. What I had to do is I had to bring this 4 to the other side so I can get it with my x. I'm going to complete the square by taking this -4, dividing it by 2, and squaring it. So I have 4 here and 4 here. So my equation is x minus 2, the quantity squared, plus y squared is equal to 4. This is a circle with its center at 2, 0, with a radius of 2. So there it is. Let's take a look at the next one. I have r is equal to -2 sine theta. Well, let's go ahead and multiply both sides by the sine of theta. See what happens. Wild and craziness. So I get r, the sine of theta, is equal to -2. But this is just y. So what I really have is y is equal to -2. So I just have a horizontal line at y is equal to -2. That's it. R is equal to -3. Well, I have a replacement for r cosine. I have a replacement for r sine. I'm disinclined to multiply this side and this side by r sine, or by sine or cosine, because then I would introduce a cosine or sine over here, so I'm not going to do that. However, I also have a replacement for r squared. So what I'm going to do is I'm going to square this side, and I'm going to square this side. And I get r squared is equal to 9. But r squared gets replaced with x squared plus y squared all day long. So I have a circle centered at 0, 0, centered at the origin with a radius of 3. Take a look at this one, where I'm going to have r is equal to the secant of theta. I don't have replacements for secant or cosecant, so I'm going to write this as 1 over the cosine of theta. Oh, this is like my other one. I'm going to multiply both sides by cosine theta. When I multiply both sides by cosine theta, I'm going to get r, the cosine of theta, is equal to 1. This is just x, so x is equal to 1. So we have a vertical line of x is equal to 1. All right, so for this one, what I'm going to do is I'm going to write from rectangular into the equivalent polar equation. What we have is x. X is r cosine of theta. That's going to be equal to 4, because that's what x is. Now, when I'm doing a rectangular to polar, my goal with polar is to have it r equals, theta equals, and if I really am hurting, then sometimes I'll have it as tangent of theta equals. We really want r equals or theta equals. The reason I said that is because I'm going to divide both sides by cosine, and so I'm going to get 4 over the cosine of theta. I'm going to replace cosine with its secant, so r is equal to 4 secant. 4 secant theta. 4 secant theta. Okay, so let's take a look at the next one. I can replace y with r sine theta. I can replace x. I'm going to write square root of 3 first. I'm going to replace x with r cosine theta. And so I'm going to end up, I'm going to have an r cosine. So, okay, let's go ahead and bring everything to one side. And I've got r, the sine of theta minus the square root of 3r cosine of theta is equal to 0. I can factor out an r. But the problem is that if I try to divide both sides by the sine theta minus 3 cosine theta, I'm going to get r is equal to 0. That is not what I want. So what I'm going to do instead is I'm going to go back up here, because that wasn't helpful. I'm going to see if maybe I can write it as doing the division. So I'm going to divide both sides by r cosine theta. Now I'm going to end up having the r's canceled, which is okay. What I'll end up with is tangent of theta is equal to the square root of 3. We can leave it like that, but it's not ideal. If we can write it as an angle, then we're probably going to try to not write it as the tangent of theta. So This is true when theta is equal to pi over 3, and that is my answer. I've got theta equals. Take a look at my next one. I have r sine theta is my replacement for y, and 2, r cosine theta is my replacement for x. So I'm going to have r squared, the sine squared theta, is equal to 2r cosine theta. Now, this one's going to be a little bit different because of the fact that I can divide both sides by r. If I divide both sides by r, then I'm going to get r sine squared theta is equal to 2 cosine theta. I can divide both sides by r, or excuse me, sine squared, so I get r is equal to 2 cosine theta over sine squared theta. And I can kind of just leave it like that. That's totally fine. If I want to break this apart, I can write this as the 2 times the cosine of theta over the sine theta, multiply by 1 over the sine theta. That's equivalent to sine squared in the denominator, which is 2 the cotangent of theta times the cosecant of theta. I'm actually okay if you leave it here, or you can go all the way to here. Let's take a look at my last one here. So for my last one, I'm going to do 2 r cosine theta squared plus r sine theta squared is equal to 1. So I have 2r squared cosine squared theta plus r squared sine squared theta is equal to 1. Now what I'm going to do is I'm going to go ahead and factor out an r squared, leaving me 2 cosine squared theta plus sine squared theta is equal to 1. Now the reason I didn't do that up here is because up here, if I were to bring everything to one side, I'd end up with, and factoring out an r, I'd end up with r equals 0, which is okay. I still would have gotten this too, but I would have had this equal to 0. This one's equal to 1, so I'm going to treat it slightly different. So then I'm going to have r squared is equal to 1 over 2 the cosine squared theta plus the sine squared theta. Now remember, my goal is to set r equals 2, so I'm going to take the square root. So r is equal to the square root of 1 over 2 the cosine squared theta plus the sine squared theta. Now, I know that I can replace sine squared with 1 minus the cosine squared theta. So let's do that replacement. Let's see if it helps at all. And so I have 1 over 2 the cosine squared theta plus 1 minus the cosine squared theta. And what I end up with then is 1 over, and this is underneath the square root still, so I'm still working with this. And so I have 1 plus the cosine squared theta, because my cosines canceled themselves out. And that's about as good as I'm going to get for right now, so there's my final answer. When we are looking at graphing polar equations, there are some polar equations that if you look at the structure, you're going to know what the equation looks like. The other way of doing it is making a table of values between 0 and 2 pi and see what happens. There are some, though, that always end up having this shape. So r is equal to theta is a spiral. R is equal to some a value where a is greater than 0. Cosine theta is going to be a circle whose diameter here is a and whose center is at a over 2, 0. If a is negative, then all that does is move the circle onto this side of the y-axis. It still have a diameter of a, and its center would now be at negative a over 2, 0. If I have a sine theta, then it's going to be a circle again, has a diameter of A. Here's where the center is going to be. If A is negative, the circle would be on this side of the x-axis. A couple of other things that we get is we get the 3-leaf rows, where r is equal to a cosine 3 theta. And so what we have is we have these petals that go at a distance of a, and it has 3 petals. If a is negative, it takes this loop and reflects it on this side, and these, of course, reflect on this side. If I have r is equal to a cosine 2 theta, then you have a 4-leaf rows. If a is negative, it doesn't do anything because it's symmetry. And we'll talk about symmetry momentarily. We have r squared is equal to a cosine 2 theta. We have this limescate. And if a is negative, which could happen, then it's going to just make the shape go like that. Okay. Now we have a 3-leaf rows, or no, that's actually for the previous one. So let me erase this. I should always remember to take those off. So we now are talking about cardioids. So if a is greater than 0, this is the shape of the cardioid. If a is less than 0, then the cardioid goes in this manner. The cardioid is going to go out a distance of negative 2a, or in this case it would be, if a is negative, it would be over here. So it would be still negative 2a, but it would be over here. And of course, when we have cosine, we also get to have sine. And so the sine, of course, would look poorly drawn like this, or like this, depending on which way it's orientated with a. The other one we have is a limacon. A limacon is basically a cardioid with a loop. The difference between the cardioid and a limacon is this. These cardioid is going to have like 3 minus 3 the cosine of theta. That's a cardioid. 3 minus 2 the cosine of theta is not a cardioid, it's a limacon. It's got a loop in it. And that's because if we look at the 3 and we have a 3, that's going to give us a cardioid. But 3 and 2 are not absolute value the same. This 3 absolute value is larger than negative 2 absolute value, so it ends up giving me a loop. If we reverse it so that it is now 2 minus 3 the cosine of theta, then we still have a limacon. It just doesn't have a loop anymore. It kind of flattens out right there. Of course, this also works for sine. Okay, let's talk about symmetry now. When we look at our graphs, it is helpful to know the symmetry before we start, so that in some cases we would get symmetry with respect to the pole. Sometimes we're going to get symmetry with respect to the polar axis. Sometimes we're going to have symmetry about the line theta is equal to pi over 2. So in other words, straight up, straight down. And that allows me to, if I know the symmetry, that I only have to graph a part of it, because by symmetry, it will be the other part. So the curve is symmetric about the polar axis if for every point r theta on the graph, the point r negative theta is also on the graph. Similarly, equation r is equal to f of theta is unchanged when I replace theta with negative theta. So let's see if that happens. So if I have r is equal to 2 the sine of negative theta, is that exactly what we start out with? And the answer is no, because sine is odd. What this is equal to is negative sine of theta. So I don't have symmetry with the pole. So then the curve is symmetric about the pole if for every r theta, that r theta pi plus theta is also on there. Similarly, that this is unchanged when we replace r with a negative r. If I replace this with negative r, I am not going to have symmetry with respect to the pole. So I know this one is not symmetric with the pole. The next one, the curve is symmetric about the vertical line. Theta is equal to pi over 2 for every point. R theta on the graph is also on the graph. Similarly, R is unchanged if I replace theta with pi minus theta. Okay, so this one's going to be a little bit of work. So I have R is equal to 2, the sine of pi minus theta. So using my sum and difference, I have the sine of pi times the cosine of theta minus the cosine of pi, the sine of theta. Now, the sine of pi is going to make that go to 0. The cosine of pi is negative 1. So what this ends up becoming is 2 times negative 1 sine theta. So I end up with 2 the sine theta. So I have symmetry with respect to the line. So symmetric with respect to theta is equal to pi over 2. What that tells me is whatever's on this side is going to have a match on this side. If I'm not sure what this graph looks like, I'm not like, hey, one of the things you could do is you could go back into its equivalent Cartesian, or if that's too much of a hassle, sometimes it is, you start finding the points by starting with an angle theta. Now I know all I want to do for theta is go from 0 to pi over 2, so I'll do 0, and then I will do pi over 6, pi over 3, oh, probably pi over 4, pi over 4, pi over 3, and then pi over 2. The only reason I'm going to go there is because I have symmetry. Now pi over 6 is out half a ring, so here's pi over 6, and half a ring is right there, so that's not very far. Pi over 4 is a little bit more, so it's like right there. Pi over 3 is the square root of 3 over 2, still not completely out one ring. Oh, there I was, not forgetting to multiply by 2, so I want to do 2 the sine of theta. Oh. So let's try this again. So 2 times the sine of 0 is equal to 0. 2 times the sine of pi over 6 is 2 times 1/2, which gives me 1. So that actually is going to go out 1. So I'm going to go pi over 6. I'm going to go out 1 ring right there. And then I'm going to do 2 times the sine of pi over 4, which is 2 times the square root of 2 over 2, which is the square root of 2, which is slightly more than 1, but less than 2. So it's about right there. 2 times the sine of pi over 3 is 2 times the square root of 3 over 2, which is the square root of 3, which is more than 1 but less than 2. So it's like, oh, I don't know, somewhere like there. And then I don't have pi over 2 happens to be, so pi over 2 sine, so 2 times the sine of pi over 2 is just going to be 2 times 1, or just 2. So this is kind of what the shape is looking like. So this is a circle. I could have recognized that also from up above because we knew that was going to be a circle. Okay. So let's take a look at the next one. I'm going to check for symmetry again. So remember, if I put in negative theta, it has to stay the same. So r is equal to 1 plus the cosine of negative theta. Negative theta is, cosine is even, so this equals the same thing as I started out with. So we have symmetry with respect to, in this case, it is the polar axis. Now, remember that is this is the polar axis. So what that tells me is what's over here is going to be the same as over here. Okay. Now, I should check it also for symmetry because we might have symmetry with respect to the pole. So if I put in a negative r, and the answer is no, I'm not going to, if I put in a negative r, it will change it. So I don't have symmetry with respect to the pole. And then the last one would say, oh, do I have symmetry with respect to the y-axis? And this is one that is going to take a little bit of work. So r is equal to 1 plus the cosine of pi minus theta. So this is going to be equal to 1 plus the cosine of pi, the cosine of theta, plus the sine of pi, and the sine of theta. This thing goes to 0. This thing goes to negative 1. So I have 1 minus the cosine of theta. This does not equal what I started out with. So I don't have symmetry in that order. So once again, I would do a chart here and see what this looks like. And what I end up with is actually a cardioid. You should check this by doing I'm going to go out 2 rings. It's going to be a cardioid. Something like that. And you should check this by doing your theta. Because of the fact that this is symmetric with the polar axis, you would start at 0 and end at pi. And then you would put that into the equation 1 plus the cosine of theta. We take a look at this. If we put in, because it's sine, if we put in a negative theta, then it's just going to give me 3 times the sine of negative 2 theta, which is still just negative 3 sine 2 theta. So I'm not going to check that one. I already know it's not going to work. So let's check with the pole. Now, one of the ways I can do it is I can replace r with negative r, or I can replace theta with pi plus theta. Remember, that's the other way of checking it. So I can replace theta with pi plus theta. Let's see if this gives me any kind of symmetry. Oh, don't forget my 2. I almost forgot my 2 there. So r is equal to 3, the sine of 2 pi plus 2 theta. So 3, and then I'm going to have the sine of 2 theta, or 2 pi, cosine of 2 theta, plus the sine of 2 theta, the cosine of 2 pi. This goes to 0, this goes to 1, and I end up with 3, the sine of 2 theta. This tells me we have symmetry with respect to the pole. That's kind of nice. So what that means is whatever happens here across this pole will happen here simultaneously. Whatever happens here has to happen across the pole, 180 or pi across the pole. So we like it when we see that. And the reason we like it when we see that is because if we have something that's happening here, it also has to be happening here. And then, of course, if something is happening here, then we have something happening here. And in fact, that's kind of what the graph looks like. What you're going to do is you're going to do theta, and you're going to start at 0, and you're going to end at pi. Now, remember, whatever happens on one side across the pole will happen on the other. You're going to put in 3, the sine of 2 theta, and you're going to fill it out that way. Let's take a look at my last one here. Again, I'm going to check for symmetry. So r is equal to 1 plus 2 cosine of negative theta. Cosine is even, so this is exactly what we started out with. And we know from up here, if we have exactly what we start out with, then we must have symmetry with respect to the polar axis. So we have symmetry with respect to the polar axis. Now we're going to do r is equal to 1 plus 2, and we're going to do the cosine, 1 plus 2, the cosine of pi plus theta. So where we are, checking for symmetry with respect to the pole. So this is going to be equal to 1 plus 2. And then I have the cosine of pi, the cosine of theta, minus the sine of pi and the sine of theta. We know the sine of theta is going to go to 0. This is going to go to negative 1. So this becomes 1 minus 2, the cosine of theta, So not symmetric with respect to the pole. And then the last one we want to check is with respect to the line theta is equal to pi. So r is equal to 1 plus 2 the cosine. And then this check is using pi minus theta. And we know that's not going to happen either, because when I expand out with the sum and difference here, that it's still going to have the sine of theta, the sine of pi, which will still go to 0. This will be a plus. So we know that's not going to be symmetric. So we have symmetry with respect to the polar axis. So what that means then is that when I go to graph this here, when I do my theta, I'm going to start at 0, I'm going to end at pi, because whatever happens on this side will also happen on this side. Now let's do this last part, which is we're finding the exact intersections of the polar graphs if they do indeed intersect. So since r is equal to r, we're going to go ahead and set these equal to each other. So 3 the cosine of theta is equal to 1 plus the cosine of theta. So I'm going to subtract cosine from both sides, and I get 2 the cosine of theta is equal to 1. So the cosine of theta is equal to 1/2. We know that happens when, and we'll just look at, we'll solve for it from 0 to 2 pi. So, of course, coterminal angles also happen. So theta will be equal to pi over 3, that's the 60, or again at 5 pi over 3. Erase that, 5 pi over 3. So r squared and r, well, that's something different. So we don't have these being able to do a quick replacement where r is equal to r. But what I can do is say, oh, look, if I square this, then I have that replacement. And so I'm going to have r squared is equal to 4 cosine 2 theta. And since r squared also equals 2, 2 is equal to 4 cosine 2 theta. So 1/2 is equal to the cosine of 2 theta. Now this is going to be different than my last one. My theta is going to be equal to pi over 3 still, plus, and I have 2 theta, 2 pi k. And the reason I have to do this is because my angle is not singular, it is a double angle. So it's going to be 2 theta is equal to pi thirds plus 2 pi k. And of course, we have 2 theta is equal to 5 pi thirds plus 2 pi k. And we know that theta then is equal to pi over 6 plus, and I'm going to leave this as pi k. And then theta is equal to 5 pi over 6 plus pi k. And as you know, I like to have the same common denominator, so I can do an easy iterations through k. So I have pi plus 6 pi k over 6. And then this theta is going to be 5 pi plus 6 pi k over 6. So now I can go through the iterations when k equals 0. Theta is equal to pi over 6. When k is equal to 1, we have 7 pi over 6. When k is equal to 2, we are outside of the interval, so don't worry about that one. Come over here, k is equal to 0. We get theta is equal to 5 pi over 6. We have k is equal to 1. And we have 11 pi over 6. So here is all of my solutions for where those two graphs intersect. Let's take a look at our last one here, and we have r is equal to r, so I'm going to set these equal to each other. So 1 is equal to 2, the sine of 2 theta. So 1/2 is equal to the sine of 2 theta. So I look on my unit circle to see where the sine is equal to 1/2. That happens when 2 theta, because that's my angle, not just theta, is equal to pi over 6, and when 2 theta is equal to 5 pi over 6. And before, plus 2 pi k, because my angle is not singular. Dividing everything by 2, we get pi over 12. And I wrote 6. That's pretty awesome. Pi over 12 plus pi k. And theta is equal to 5 pi over 12 plus pi k. Again, we're going to make it the same common denominator. So I have pi plus 12 pi k over 12. And theta is equal to 5 pi plus 12 pi k over 12. So go through the iterations of k equals 0, k equals 0. And I've got theta is equal to pi over 12. And here I've got theta is equal to 5 pi over 12. K is equal to 1. And over here I'm going to get to 13 pi over 12. K is equal to 1. And I wrote 2 because I'd really just like 2. K is equal to 1. And I'm going to have 17 pi over 12. And of course, when k equals 2, I am too large. So that's it. This is polar graphs and equations in a nutshell.